Okay, so in the last few lectures, we saw how you can use these pKa values to determine the relative strength of an acid. Here we're going to talk about qualitative features in a molecule that would lead one to be stronger than the other, right? So we're trying to put some reason as to why those pKa values are trend the way that they do. Um, Okay, and one of the big things that we're going to think about when we're assessing the relative strength of an acid is to talk about the stability of the conjugate base, right? So that acid is going to donate a proton. What's going to be left over is the conjugate base. If the conjugate base is really stable without that proton, that's going to be a strong acid, okay? So formal charge is going to be a big thing here. If we want to look at these two examples here, we have HCl. What's the conjugate base of HCl? Well, that's just the chloride ion. And then what's the conjugate base of this acid here if it donates that proton? This is this carbanion. So the difference between these two acids is the stability of the conjugate base. More importantly, which one is more stable at holding that negative charge? Okay, chloride ion is way more stable than a carbanion, right? Chlorine is pretty cool with having a negative charge, a formal charge of -1, whereas carbon really doesn't want a formal charge. So whenever we're asking ourselves which is the stronger acid, we're really asking ourselves what's the more stable conjugate base, okay? So there are going to be 4 factors that we're going to look at here, and these are in sort of order of decreasing importance, actually. So this is the most important thing, is the type of atom that's going to carry that formal charge. Then there's going to be resonance stabilizing effects. If that formal charge is stabilized through resonance, that's good. There's going to be this factor called induction, and we'll talk a little bit more about what that is. And then the last factor is the type of orbital where that charge resides. That's kind of the least important thing, but nonetheless, it'll be very important. You can use this little acronym ARIO to remember that order here: atom, resonance, induction, orbital. So what do I mean by atom? So again, the identity of the atom that's going to carry the charge has a lot to do with how stable the charge is. More electronegative atoms are going to be more stable with a charge, i.e. a stronger atom. This is especially important when you're comparing atoms in the same row, right? So if I'm going to look at the difference here, again, let's just practice here. We got to get good at drawing our conjugate bases. So everybody take a second and draw the conjugate base of these two molecules. Again, for butane, it'll be that carbanion. For propanol, it will actually be the oxygen that bears that negative charge. Carbon and oxygen are in the same row. So the one that's going to be the more stable conjugate base is the one where the charge is held on the more electronegative atom. So in this case, propanol is a much stronger acid than butane because that negative charge on the conjugate base will reside on oxygen, which is more electronegative. Okay. So now, what about when they're not in the same row, but instead in the same column? So let me just So what if instead I was comparing this molecule here, which is sulfur, which has a sulfur hydrogen bond, to my propanol? So again, if I'm going to draw my conjugate base, I would see that that negative charge is now on the sulfur atom in my conjugate base. So when they're in the same column as with sulfur and oxygen, it's actually the larger atom that's more stable. So it's a size argument then. The bigger the atom is, the further away its valence electrons are, and so the more room they have to spread out, there's less electron-electron repulsion. So bigger atoms are more stable holding a formal charge than our smaller atoms. Okay, so in this case, it would be the thiol that's the stronger atom, stronger acid, because sulfur is a larger atom, more stable, holding that -1 formal charge. All right, so if they're in the same column, you compare electronegativity. I'm sorry, when they're in the same row, you compare electronegativity. When they're in the same column, you compare size. The larger one is more stable, i.e. the stronger acid. More stable conjugate base, i.e. the stronger acid. All right, number 2 is resonance. So is that charge resonance stabilized? We talked a lot about resonance last lecture. Given these 2 examples here, you should be able to identify the fact that one of these has resonance available to it and the other one doesn't. Right, so here we have our allylic lone pair. So that's one of these structures that exhibit resonance. So we're going to look at the conjugate base of these 2. For ethanol, it's that, and for acetic acid, this is my conjugate base. In acetic acid, this negative charge is stabilized by resonance through this bond right here. So acetic acid is going to be the stronger acid because its conjugate base is resonance stabilized. Okay, so this is now that second factor that will allow us to qualitatively determine acidity. So now induction. What does that mean? So induction is an ability of an electronegative atom to stabilize charge, okay? Kind of like pulling electron density onto itself. So I think the best way to illustrate this is with an example. So notice here we have our acetic acid again. The difference in each one of these molecules is I'm adding more and more chlorines onto that. Chlorine, remember, is a nice electronegative halogen. And now let's look at what's happening to the pKa's as I'm adding more and more chlorines on. Right, so which one of these is the strongest acid up here? Remember, strong acid means low pKa. So the presence of these 3 chlorines is really what's making this so much stronger than acetic acid. So if I'm going to draw my conjugate base again. So the question is like, why is this so, why is the structure on the right so much more stable than the structure on the left? Because again, that's what we mean when we're saying strong acid. We're talking about a stable conjugate base. So those chlorines are helping to stabilize that negative charge. Again, in both of these, you have this resonance network that's stabilizing the formal charge. And that means that that negative charge is being spread out through that, that resonance network, through those lined up p orbitals, right? By having these chlorines here, these electronegative chlorines, they're going to, through induction, kind of like sucking that electron density onto itself even more, they're going to stabilize the negative charge in that resonance structure by pulling some of that electron density onto itself, right? Spreading it out even more throughout the molecule. So that is what we mean by induction, is an electronegative element's ability to help stabilize negative charge by helping to spread out that electron density. So the presence of these strong electronegative groups will also increase the acidity of a molecule. All right, and the last one is has to do with the orbital that's going to be bearing the negative charge. It's going to hold that lone pair. All right, so if we look at these 3 here, This carbon is sp3 hybridized in ethane, sp2 hybridized in ethylene, and sp hybridized in what's called acetylene. So if I'm going to be a little bit lazy in terms of how I do this and just erase it on the structure. So if I donate an electron here, that means that there's going to be a lone pair living in an sp3 orbital. Likewise, if I got rid of this hydrogen here, if that was donated in an acid-base reaction, I would have a lone pair living in an sp2 orbital. And then lastly, if I donated this electron here, I would have a lone pair that's living in an sp orbital. Okay, so it turns out that the sp orbital, that sp orbitals are smaller, they're held more closely to the proton than our sp2, than our sp3. So we can just say, you know, the evidence is in the pKa values here. The acetylene is actually a stronger acid than is ethylene, than is ethane, which is just a terrible acid. Okay, so the fact that that lone pair, that formal charge, I guess let me draw that in as well. Not only is there a lone pair, but also that negative charge. The fact that that negative charge is being held in an sp orbital is more stable than if it were being held in an sp3 orbital. This is the least important of all the different effects that we've talked about here, but nonetheless does play a role. Okay. Okay, so then this is an order of importance here is, again, the type of atom. That's the most important thing in determining acidity in a molecule. Then resonance, then if there are any inductive forces, and then the type of orbital that that atom is found in. So let's take a look at an example here. We have 3 protons, and we want to rank them in terms of their acidity. Which one's the most acidic? That's going to get a 1. And then we're going to rank all the way to number 4 will be the least acidic proton. Okay, so again, first of all, we got to look at what these are bound to, because it's all about the stability of the conjugate base. So here, this hydrogen's bound to a carbon, this hydrogen's bound to a carbon, this hydrogen's bound to a carbon, and this hydrogen's bound to an oxygen. So right off the bat, which one can we tell is going to be the most acidic proton? Atom is the most important factor. So this hydrogen here is going to be the most acidic. So then when we go and compare, so we got this one down, awesome. Now let's compare our other 3. They're all bound to carbons. So I can't use this type of atom rule. I got to move on to the next one. So are any of these going to be resonance stabilized? Maybe actually this would be easier to see if I actually replaced each of these with a lone pair. Which one of these is resonance stabilized? Hopefully you've been able to identify this allylic lone pair pattern here, right? Allylic lone pairs are resonance stabilized. So in fact, and then I guess I just want to point out explicitly, this one is not. It's a vinyl lone pair. It's too close to that double bond to be resonance stabilized, right? You got to be separated by 1 sigma bond. So in this case, if I'm going to rank number 2, that would be this hydrogen here. Okay. So now comparing, so got that one checked off, awesome. So now comparing A and B, which one is going to be the most stable? The next level would be in, so they're both the same atom. There are no more resonance stabilities here. So then I can look for induction. These fluorines are actually too far away. They've got to be closer to that site. I mean, they're not doing nothing, but nonetheless, they'd have to be closer to that site. So wait, why am I doing that example? It's just confusing. All right, so then these are the four factors that we need to consider when we're assessing the qualitative stability of, or the qualitative acidity of various molecules. The most important factor being the type of atom that's going to carry the charge. Second most important, is there any resonance stabilization? Third, any inductive effects? And then fourth, what type of orbital is that charge going to reside in? Okay, so let's take a look at this molecule here and see if we can't determine which one of these protons is going to be the most acidic. I have 1, 2, 3, 4 protons that I'm considering here. Which one is going to be the most acidic proton? So again, that first step is I'm going to look at the type of atom that would bear the charge if this proton gets removed. So for hydrogen C, it's a carbon. For hydrogen A, it's a carbon. For hydrogen B, it's a carbon. And for hydrogen D, it's actually an oxygen. Okay, so right off the bat, I can tell which one's going to be the strongest, the most acidic proton, and that's going to be hydrogen D because it's bound to that oxygen, right? Oxygen's more electronegative than carbon. It's going to be more happy to hold that negative charge. Cool, so that one's done. So now let's see if we can't compare these other three, A, B, and C. Well, they're all bound to carbon, so I can't use rule 1. What about rule 2? Are any of them going to be resonance stabilized? Perhaps the easiest way to see this is to actually remove these hydrogens and replace them with lone pairs. Are any of these lone pairs resonance stabilized? Is this negative charge going to be resonance stabilized in any of these positions? Hopefully you guys were able to notice the allylic lone pair pattern. That was one of the patterns that we saw last time will exhibit resonance. So indeed this carbon, or this hydrogen right here, is resonance stabilized, so this is the second most acidic proton. Notice that this one is not resonance stabilized. It's too close to that double bond. It's in what's called the vinyl position. You have to be in the allylic position to be resonance stabilized. One removed. There's got to be that sigma bond in between. All right, so then lastly, I got these two here, and I got to determine which one is going to be more acidic, A or B. There are no resonance effects for these two. Likewise, there are no inductive effects. There's no electronegative groups that are sitting closely that can pull electron density. So then we get to the orbital type here. This carbon is in an sp2 hybridized orbital, whereas this carbon is sp3 hybridized. So that would make this the next most acidic proton. And then finally, hydrogen D is the least acidic proton. Okay? So again, that's how we sort of compare all of our factors. First, we look at atom, then resonance, then induction, then the type of orbital. Some acids actually start out with a formal charge of +1, right? When they lose their proton, they become neutral. In such cases, we can actually use our REO rules to see if that positive charge is going to be stabilized in any of them. The less stable positive charge would be the stronger acid, right? Whichever one of these two is we consider to be less stable means it wants to get rid of that hydrogen even more. All right, the last thing that we can do, now that we've gained this ability to qualitatively assess the strength of acids, is to remember how we were using pKa's to determine which direction an acid-base reaction favored, whether it favored reactants or products. Remember, these reactions favor the formation of the weaker acid, right? Stronger acids win. So here we can go and look at this reaction and then try to qualitatively assess what direction this reaction will go, whether it favors products or reactants. So the first thing we got to do is identify what my acid is and what my base is, right, on the left-hand side. This is the proton that's being donated. Notice how it's lost over here. So this is going to be my acid. This is going to be my base. So then my conjugate base is over here, and conjugate acid is over here, okay? So I want to figure out which direction this reaction lies. It's going to lie in favor of the weaker acid. If I could look up the pKa values of this, we could be done, right? But the whole idea is that we're going to do this qualitatively based on what we know. So the question now is, when we're thinking qualitatively, we're actually thinking about the bases and which one is going to be more stable. So if I'm looking at my bases, my base and my conjugate base, which one is more stable? That will tell me which acid or conjugate acid is stronger. Here, notice that we have, what's this pattern? The vinyl lone pair, right? And we have that in both cases here. The difference is one of the atoms on top is sulfur, one of the atoms on top is oxygen. Which one is better at stabilizing negative charge? It's going to be the sulfur, right? Because it's larger. So this is more stable. This is less stable. And so which one's stronger then? My conjugate acid or my acid or my conjugate acid? In this case, it's the conjugate acid because it has the more stable base, right? So this reaction will lie in favor of my reactants. Okay, so we can use this qualitative ability to also determine which way which direction is favored in a given acid-base reaction.